Good morning and welcome to the second day's activity. Before I introduce the speaker, I'm supposed to say a few words about the topic of his talk, which is in the domain of geometry. There is a, I want to say, so you have this notion of topological space, okay? And it can be explained as doing geometry on rubber sheet. The exact size or proportions and so on of the sides and so on, they don't matter. What matters is some intrinsic property which is invariant under stretching and shearing and so on, without poking holes or cutting and doing something very violent like that. However, when you do geometry, you have to be careful. You just cannot deform something and then hope to have the same geometry. The surprising thing is that sometimes you may study very highly geometric property, but that informs about the topology of the object you are studying. Okay? In some ways, therefore, at least in some very restricted class of cases, geometry determines topology. Okay? If you know some geometric information, then you can say a lot about the topological type of the object you are studying. So with this brief introduction to the interaction between topology and geometry, I will now introduce the speaker. It's a pleasure to introduce Professor Harish Seshadri. He did his MSc, integrated MSc at IIT Kanpur, and then he did an MS degree at Johns Hopkins University. After that, he did his PhD at State University of New York, Stony Brook. He is currently faculty member at Indian Institute of Science. So before I hand over the mic, I request all of you to please switch off your cell phone or put your cell phone in silent mode. Thanks to Sundar for reminding me.
So it's a pleasure to thank Professor Raghavan for inviting me here. I mean, it's very obvious that he has taken so much trouble to see that everything runs smoothly. So I'm glad to be part of this. And I hope I'll be able to say something which is both interesting and comprehensible. So I tried to keep my talk as elementary as possible. So let's see how it goes. Now, as Parmesh said, the ultimate goal of this talk is to link two seemingly disparate aspects of geometry. Here I'm using geometry in a very broad sense. Geometry in the sense it's part of mathematics where you are able to visualize figures and so on. However, that's too vague. As Parmesh said, there is one part of geometry is actually called topology, where you don't care about things like angles and distances and area and curvature and so on. All you care about is what are the properties which are invariant when you stretch and bend an object. The other part pays a lot of attention to this finer information, namely distance and length of curves and things like that. So now for both of this, there is an underlying class of spaces, geometric spaces, which one usually deals with. Those are called manifolds. But rather than define a manifold, what I'll do is, I'll start with some familiar objects and discuss these notions in the context of these familiar objects. So the objects I'll talk about are Is it visible? Okay. Yeah. So anyway, let me write it. So I'll start by discussing curves in R2, which is the simplest possible thing one can imagine. Then something slightly more complicated would be a curve in R3, and something which is significantly different is a surface in R3. So I'll come to this next. So let's start with this, a curve in R2. So for me, a curve in R2 is a function is just a smooth function from an interval into R2. So here smooth is somewhat vague. So more specifically what I mean is, see, you can write sigma as in terms of components. It has two components, sigma 1t. This is basically what you call a parameterized curve in high school or early undergraduate studies. So the parameter is t. So it has two components where each component is just a function from an interval into real numbers. And when I say smooth, I just demand that these real valued functions of real variables are infinitely differentiable. Actually, infinitely differentiable is a bit too much. For the purposes of this talk, maybe 3 times differentiable is good enough, but let me just say that we require that sigma 1 and C2 have derivatives of all orders. Okay, then, but I want to rule out things like this. Since I'll be talking about geometric constructions. See, in the case of, if one is just interested in topology, one need not even bother about derivatives and so on. One would just require a continuous curve to start the study. But here I want to talk about both topology and differential geometry. So I would also like to rule out, even if a curve is smooth, I don't want it to look like this. This can be the image of a smooth curve in R2. So I don't want it to have a sharp corner like this. So what I'll do is, we will restrict to this. By the way, you can get a curve like this just by taking, for instance, this, if you take, so let me give a concrete example of a curve which looks like this. If you look at the curve, minus, this is minus 1 to 1. Which has these, sigma 1 is this, sigma 2 is this, then the image of this curve is going to look like this. It will have a sharp corner at the origin. So I don't want this kind of thing. So it's easily avoided by this following restriction. We will restrict to curves such that sigma prime t is equal to sigma 1 prime t, sigma 2 prime t. This is not the zero element for any t. So in this case, when t equal to 0, it gives rise to the derivative vanishes when t equals 0. That's the reason for this kind of cusp forming. So let's take it as a small simple fact that so let's say fact, if this condition is satisfied, then the image of the curve has no has no corners or cusps. So these are all, this is a very vague statement, but the point is it can be made mathematically precise. Just this simple condition that the derivative is non-zero will ensure something like this does not happen. So this statement can be made precise, but let's assume that. So such a curve is called a regular curve. So we'll assume that all curves are regular. It's just a technical technical thing to avoid this. All right. Okay. So now, so we want to investigate, we want to start by investigating the geometry of curves. So what exactly do we mean? Well, right. So basically we want to say, so given two curves in R2, we want to say when they are pretty much the same thing. So this statement is extremely vague because the same, what do we mean by same, and what kind of criteria are we looking for? Well, both can be made precise. So here is the notion of sameness. So if you have two objects in R2, when would you like to say that they are geometrically the same? Well, if you can just move one to the other, if you can just translate one object and then rotate it, so that after translation and rotation, both of them coincide, then obviously we would like to say that there's the same thing. So because when you translate an object, you're not really stretching or bending it. You're just literally moving it from one spot to another. And rotating also doesn't change really any geometrical property of the object. So the basic notion here is that of a rigid motion. Rigid motion of R2 as a map T of x equal to ax plus b. This b is the translating vector. So b is just an element of R2. Now a is supposed to be correspond to the rotation. So a is a rotation matrix. So this is just an orthogonal matrix. All of you probably have seen this. A is a 2 by 2 orthogonal matrix. Okay, so this is the basic notion of equivalence, at least for the first part. In the second part, we'll come to another notion of equivalence. Two sets, so this is one definition. Two sets S1, S2 are said to be congruent if there is a rigid motion T of R2 such that TS1 equal to S2, which is exactly what I said earlier in words. So you just start with S1, you rotate it, then you translate it, you'll end up with S2. So now we ask the question, when are two curves, so given two curves, so let's take it as what I'm about to discuss, let's take it as the motivating question. Given two curves, when are the images congruent? So the key point is, what do we mean by when? We want to basically, so we have these two curves. I want to associate some numbers to this curve and this curve. And then I want to say that if these numbers are the same, then the two curves are congruent. That's the idea. So let's start with a simple, so this is called, of course, this is the usual thing in mathematics. Whenever you want to find out if two objects are the same in whatever notion of sameness you're dealing with, you look at properties which are preserved by that equivalence and then study those. So here, for instance, the simplest thing one can think of as if one curve is obtained by a rigid motion applied to another curve, then one immediate thing comes to mind, property which should be preserved. That is that of length. So, yeah, before I go to that, so let's just discuss some couple of examples. Any curve congruent to a straight line segment is again a line segment. This is immediately clear. So if you start with, say, if this one represents the image of this is a straight line, and if you apply a rigid motion to that, it will again give you a straight line. Because after all you're doing is multiplying by a matrix which will take straight lines to straight lines, and then you're applying translation. Similarly, any curve similar statement for circles. So if you start with a circle and apply a rigid motion, whatever you get will also be a circle. But the point is that we would like to read this information just by looking at one curve and getting some invariance out of that. Okay. So, for example, the invariance we get should be able to recognize whether the curve is a straight line or a circle. More generally, it should be able to recognize, given two curves, when are they related by a rigid motion. So, let me make this precise actually. Image is congruent. More precisely, what we want is, I've been talking about images, but to be very specific, let's treat them as functions. So, I want this function composed with t to be equal to the other function. Of course, the immediate question is that the sigma 1 is defined on some interval ab and this is defined on some other interval cd. So, the first thing is whether they even have the same interval of definition or not. Can we ensure that after some adjustment whether they have the same interval of definition or not. So, that is easily taken care of by the next point, which is about length. So, let us talk a bit about length of curves. Now, before that, let me talk a bit about a technical stuff about reparameterizing a curve. See, as I stated, a curve is a function from an interval into R2. So, the real object of interest is not exactly this function, but rather its image. See, the same a circle, we know that a circle can, for instance, a circle, if I take from 0 to 2 pi, a circle can be written as cos t sin t. The image is a circle. But I can also write the circle in other ways, right? I mean, instead of this, I can say, for instance, well, the simplest thing is I can just change. I can, for instance, just make a trivial change. Instead of considering cos t sin t, I consider cos 2u sin t sin 2u, but change the domain also, 0 to pi. The image will still be the same, but this sigma has changed. The formula for sigma has changed to the new thing, and of course, the domain also has changed. So, the real object of interest is the image, not the specific formula for the curve. So, we have quite a bit of freedom in writing the exact formula for the curve. That is what this thing has to do with, reparameterization. So, technically, what is a reparameterization? Well, it is just a map of two intervals. A reparameterization a curve sigma is a function phi such that there are some technical conditions about phi. Phi has to be also differentiable and derivative should be non-zero and so on. So that phi is smooth and phi prime not equal to 0 at any point. So don't worry too much about this part. Then this new thing, sigma composed with phi, is now a function from here to here. This is a new curve. Strictly speaking, it's a new curve because it's a new function with a new domain. But actually the image of this gamma and the image of the original sigma are the same. So if this is CD, maybe, so this phi takes this interval to this interval, and then sigma takes it to R2. So the image is going to be the same. Phi is smooth, phi prime not 0, and of course I should also say that phi is smooth and bijective. So we can work out what phi is in this case. It's just multiplication by 2. Now, right. So what did I want? Yeah, okay. So here are some facts about reparametrization. So which are easy to check. Facts 1. A regular curve, remember regular just meant that the derivative is not the 0 vector at any point. A regular curve can be reparametrized so that it has, if you think of a curve, if you think of t as time and sigma t as the path of a particle in R2, then sigma prime will of course be the velocity of the particle, and norm of sigma prime is what is usually called speed. So this is called the unit speed condition. This is a simple exercise, but anyway, it involves some checking. So the fact that the derivative is not 0 can be, by the way, yeah, what I really mean is not that the original curve, if you call sigma, so here the condition is that sigma prime t is not equal to 0. But here I've written it this way. What I literally mean is that gamma, the new gamma has derivative 1. So the statement is that there is a phi such that when I consider this, gamma prime u has norm 1. But I've written it in terms of the original one itself, just so that we don't invoke too much notation. So I won't mention this gamma at all. I assume that sigma has been reparametrized so that this condition holds. Second thing is that, of course, this involves a little bit of work to see, not that difficult. But second thing which is easier to see is we can assume A is 0. See, the sigma was from AB to R2. So we can assume A is 0. just by considering sigma of t minus a. That's all. So when t is a, so this new function is now defined on 0 to b minus a. Okay. So just make this change of variable. Change of variable is the same thing as a reparameterization. So just make this change of variable and you have this. So the upshot of all this is that now let's come to length. So because of the second thing here, I'll always assume the starting point is 0. So I might as well put this 0 to b R2. We have all seen this. This is just norm of the derivative integrated over the whole interval. So if sigma has unit speed, then this quantity is 1, length of sigma would be just b. So this b would represent length. Okay. So now let's return back to our discussion about rigid motions. So if sigma 1 and sigma 2 are congruent, then they have the same length. Okay, so this is quite clear geometrically. I mean, not much to say. If you start with a curve and if you just translate it and rotate it, of course its length doesn't change. But it can be checked through computations as well. So they have the same length. So in particular, if the starting point is the origin, then this b represents length. So both are defined on the same interval. So in particular, if both are unit speed, if you put unit speed parameterization on both, then they are defined on the same interval 0 to L, where L represents length. So then this statement that I made earlier makes sense, that so then we can ask, when T of sigma 1 T we can ask when. So if they are congruent, they are defined on the same interval and so on. But here the thing is, we can ask, but is that enough? We can ask when this happens if sigma 1 and sigma 2 are unit speed and have the same length. So the converse question. Here we come to something interesting. Of course, having the same length is certainly not enough to ensure that they are congruent. We need something finer than that. So here we come to the basic notion of curvature. So Amazingly enough, this single quantity, this plus the length, turn out to completely determine the shape of a curve in R2. Just two of these are enough. So curvature, well, until what point is my talk? 11:10. Okay, fine. So, okay. So curvature of a plane curve. Now, all right. Now this is done. Right. It's, well, I can just give one line definition. So let sigma from 0 L be a unit speed curve. Then the curvature is again a function of sigma. Curvature of sigma is a function defined on the same interval. And k is just defined to be the norm of k of t. K at time t is just defined to be the norm of sigma double prime t. That's it. If you think of sigma prime as the velocity, then of course this is the acceleration. So it's just the norm of the acceleration vector. So the way we are defined curvature, k of t is always going to be greater than or equal to 0. So in this case, at least by this definition, it doesn't have a sign. But one can also get signed curvature. Maybe I'll come back to that later. So right now this is good enough. So now let's just check some examples. Curvature of a straight line. So let's take an infinite straight line. So sigma t is a straight line passing through the point V in the direction V. Doesn't matter anyway, whatever straight line it is, you'll get the same answer. But this represents a straight line in the passing through t in direction V. So of course here sigma double prime t equal to 0. So k of t is 0. Identically 0. Which is expected. A straight line should have no curvature. Now let's look at a circle of radius r and center, let's say, the origin. So in this case I can parameterize it. Oh, by the way, here since I made a big fuss about unit speed parameterization, actually here I should put it like this, TV plus P perhaps. This V is supposed to represent a velocity, the tangent vector, and P is the point. So since I made a big fuss about unit speed, here I should, the velocity of this is just, sigma prime is just V, it's a constant. But I would want that to be 1. So I might as well throw it in here. Because this formula for curvature that I've written is valid only under this assumption, unit speed curve. Valid in the sense, of course, for any curve I can define this, but it won't have nice properties. When it's unit speed, it works out fine. When it's not unit speed, starting from this, one can work backwards and get a different formula for the curvature, which is actually quite useful in practice. Because if you are given a curve, it's quite a messy business to make it unit speed, to find the right parameterization. So typically, this formula is not so useful in calculating curvature. But for theoretical purposes, this is good enough. So let's continue with this. Now, circle of radius r, I'll just use the usual parameterization. So I have to put an r here, sine t by r. And t, the interval is, well, it's 0 to 2 pi r. So this way it has unit speed, because the first derivative is just minus sine t by r cos t by r. Norm of the first derivative is 1. And the second derivative is, well, it's 1 by r minus cos t by r. So if I take norm of the second derivative, I'll get 1 by r. Therefore k of t is just 1 by r, it's a constant. So of course, as the circle radius becomes shrinks, the curvature becomes larger, which is also expected. Now, the amazing thing is that, as I said, these two invariants are good enough. So the length of a curve and this curvature function will tell you when two curves are congruent. Why is it surprising in the first place? Well, surprising because why stop at the second derivative? You can keep on going. You can take third derivative, take the norm, and so on. So potentially all of this could arise. There could be infinitely many things one can calculate. But it turns out that just two of these are enough. Calculating just this. Now, so here's the theorem, which I'm not going to prove. It's basically the theorem, if you know ordinary differential equations, existence and uniqueness theorem. Actually, the uniqueness is the relevant part here. If you know the uniqueness part of the Picard's theorem in ordinary differential equations, it's not difficult to prove this. So, right, let me state this. Before coming to that, let's just observe that curvature is indeed preserved by rigid motions. If t is a rigid motion, I said for length, the fact that length is preserved by rigid motions is kind of obvious, but for curvature, since the definition is not so geometric, after all, what does second derivative mean? It is possible to define curvature in a more geometric way, at least more geometric than this. But the way I have defined it, it may not be immediately clear, but let's just check that this is such that t of sigma 1 equal to sigma. If you have two curves which are related by a rigid motion, then the curvature of the curve sigma 2, which I'll denote, just put a subscript here at t, is equal to the curvature of, oops, not here. That's okay. They have the same curvatures. this is quite clear, because if you it's just a matter of taking second derivatives. How do I calculate curvature of sigma 2? Well, I would take second derivative of this and then finally take norm. Now, if I want to take second derivative, well, I'll just have to differentiate through this. But t, let's start with first derivative. T of sigma 1 t is just A, the orthogonal matrix, times sigma 1 t plus B. So when I differentiate this with respect to t, d by dt of this, well, this is a constant matrix. So I don't have to worry about this. I just have to differentiate this. This is a constant vector. So anyway, its derivative is 0. So I end up with this. So if I do it once more, again the same logic. So A sigma 1 double prime t. So it's A sigma 1 double prime t. And then I have to take norms. But remember that this was an orthogonal matrix. So an orthogonal matrix preserves length of vectors. So norm of A times V is just norm of V. So this is just sigma 1 double prime t. So therefore I get this. So now I'll state the theorem. So it's so the theorem is that two curves, of course when I say curves I always mean regular curves. Two curves in R2 are congruent if and only if they have the same length and curvature. So this is sort of as satisfactory a result as one can ask for. When two curves are congruent, is just given by these two numerical quantities. One is a single number, length, the other one is a function, curvature. All right. So now now let me briefly discuss a very interesting theorem in curves in R3. Okay, so here I won't be able to say much. I mean, I won't be able to go into details, but what I'll talk about are, this is the first instance of topology entering into the picture, as opposed to all this had nothing to do with topology as such. Here you'll see some topology in play. Curves in R3. So I'll consider a simple closed curve in R3. So pictorially, well, it's just a curve, it's a loop. It's a curve which goes back and meets its starting point, but it does not intersect itself at any other point. So it's like a rubber band. Yeah, it's exactly like a rubber band in R3. Simple closed curve in R3 is a map from AB to R3. Smooth again. All three component functions are smooth. Here it will have three component functions. All of them are smooth. and I demand that sigma T1 equal to sigma T2 if and only if T1 equal to A or B, T2 equal to A or B. So only they meet only at the endpoints is what I'm saying here. And also there's one more condition. See, when they meet back at the endpoint, they can meet like this. I don't want that. So at the meeting point also it should be smooth. So let me throw that condition also. So all derivatives at A for all n. So this is the nth derivative. The derivatives at A and B agree. So we have a nice closed, is basically a rubber band in R3. Now, except that a rubber band is slightly misleading because of this that picture there. This is too light. Maybe can you put off the, yeah, this is better. Yeah, so this, for instance, is a simple closed curve in R3. It satisfies all the conditions that I wrote down. It is smooth. It does not touch itself at any point except at the, so you have to designate some point as the starting point and the ending point. So it just closes upon itself. But the only, why, of course, it's not a rubber band, because it's knotted. That is a key point here. Okay, so that complication can arise, and that is the object of interest here. The fact that you can have a knotted curve in R3. How is now, okay. Yeah, can you please put on the lights? Now, here's a topological notion. Two knots. So, a simple closed curve in R3 is one. So, this is also called a knot. Well, why different terminology is used is that usually when we say simple closed curve, we do allow intersections on the inside, I think. But here, the way I defined it, this and that are the same. Such a curve as a knot, and so here's a definition. Two knots are isotopic. One can be continuously deformed to the other. Now, here I am being somewhat vague. What there are two notions of when deformation. See, what a knot is you can forget about R3. You can just think of a knot as a topological space. And you have two topological spaces, basically the two knots. We can ask when they are homeomorphic, in case you have seen homeomorphism. But that's not what we visualize. What we here, when I say continuously deformed to the other, it literally means that. So imagine that you have a knotted curve. You are standing with a knotted curve, and then you are given another knotted curve. Somehow by moving this way, that way, can you get one from the other? So for instance, if I'll as a trivial example, since I'm not a topologist, in any case, I can't draw pictures. So I'll just have to give a trivial example. So for instance, if you take well, yeah, so imagine it in 3 dimensions. So whatever. So if you take this curve, this can be just by stretching and pulling, you can make it into a circle, right? So then we say these two are isotopic. But there are far more complicated things. You can imagine a rubber band. You are not allowed to cut the rubber band, but you can just put it one inside the other and so on. But can you get from one to, can you sort of make the rubber band back to its original shape is the question. And you can, if you are not allowed to cut. But if you start with something like that, obviously there's no way of getting this back to a circle without cutting that, right? Whatever, however much you may pull or stretch, you can't move from there to here. So that knot is not isotopic to a circle. So there's a whole subject of mathematics called knot theory, devoted to studying when two knots are isotopic. But here we are interested in the relation with differential geometry. So now here's a very interesting theorem. One can define, so here I'll be a bit vague. One can define the curvature of a space curve. Usually when we say space curve, we mean curve in R3. When we say plane curve, we mean curve in R2. One can define the curvature of a space curve in a similar way. To that of plane curves. Well, similar way means it's not literally, I mean, you don't just take the second derivative and take the norm. You have to do a bit more. So I won't go into the definition, but so I'll just put it within quotation marks. Similar. So you will end up getting a curvature function kt from 0L to R. Now here's a theorem. If a curve, if a knot is not isotopic to a trivial knot means i.e. a circle like this, then integral of k of t dt 0 to L greater than 4 pi. So this is called, was proved by two mathematicians, Ferry and Milner, perhaps in the 1960s. So what does it say? So it says that you can basically, if the knot is really knotted and you calculate its curvature function, then it should have this thing. Now if if you do it for the circle, if you calculate the same quantity for the circle, curvature of the circle is 1, then the length is 2 pi, so you'll just get 2 pi. So the moment a curve becomes knotted, suddenly there's a jump it has to become 4 pi. That's, so what, however much you may try to reduce curvature, suppose you start with a knot and you make it sort of, how do you reduce curvature? Well, you make it very straight line looking. So you try to make it look like straight lines and so on. Whatever you may do, at some point there will be enough curvature which will make the integral very large. Not very large, integral suddenly jump up. So this is a typical example of a curvature topology kind of thing. On the one hand, the assumption is topological. A knot is, you assume that it's not a trivial knot. Conclusion is that some geometric quantity has to behave in a certain way. So if its knot is not trivial, then somewhere curvature should accumulate is the point of this. Enough curvature should accumulate so that it suddenly jumps up beyond 4 pi. See, here it was 2 pi. There's a gap of 2 pi. It just all right. So now let me quickly try to talk a bit about surfaces in R3. So actually the real beginning of differential geometry started with the study of surfaces, not with curves. Even though even with curves there are many interesting things going on, like this theorem which was proved as recently as 1960. But I'll shortly explain why. But the real study of differential geometry starts with surfaces in R3. So what is a surface? Well, we all know what it is intuitively. So let's define it. So first I'll define what I'll call a local surface. Local surface just means it's an image of so it's a map. See, for a curve I start with a map from an interval. Here I'll start with a map of an open set in R2 into R3. Such the usual conditions. Phi is smooth. Now when we say smooth, see, phi has 3 components. Phi of uv, the coordinates I'll take to be uv. So phi 1 uv, phi 2 uv, phi 3 uv. So these coordinate functions, phi 1, phi 2, phi 3, they are real valued functions. So let me just write phi I. And I demand that they are smooth functions. They have partial derivatives of all orders. Partial derivatives of all orders exist. And again, there is an analog of, see, we had to impose the condition that the curve is regular, but here there's an analog of that which is slightly more complicated, which is that the Jacobian matrix phi is regular, i.e., the matrix del phi 1 by del u del phi 1 by. this matrix has, well, it's a 3 by 2 matrix. So the maximum rank it can have is rank 2 at every UV in. So if you don't understand this, why this is required, well, you just remember that this is required for the same reason that we had to impose regular for a curve, regularity condition for a curve. Namely, this condition will ensure, it's a fact that this condition will ensure that the surface does not develop sharp corners like this. Imagine this is the XYZ plane. You can have a surface which looks like this, but we don't want this kind of thing where it suddenly comes and forms a sharp edge. Everywhere it should be smooth. This kind of condition that this has rank 2 will ensure that the image will not look like this. Everywhere it will be smooth. Just demanding that you have a smooth function is not good enough. Even if the function is smooth, the image might have look like this. So we would need this additional condition. So this is a local surface. Now, what a surface, when I just say surface, I mean is a set so that every point in it is every point in it has a neighborhood which is a local surface. So, so as an example, if I take the two-dimensional sphere, my surface is S2 inside R3. So this is the set of points at that x squared plus y squared plus z squared equal to 1. Well, if I go by this definition of a local surface, so if I take any point, I should be able to find a function phi mapping some open set in R2 into this and so on. So if I take any point here, I can put it in the upper hemisphere. This upper hemisphere can be realized as the image of some such phi. And similarly, anything here can be realized as the image of some such phi. Of course, you are left with what to do with this point. So you have to put lots more like this. Just two of these will not suffice because these points will be missing. So you have to take a bit more care. At any rate, the point is that the whole sphere can be broken up into pieces, each of which can be realized as images of all those phis, different phis. Of course, the whole sphere S2 cannot be realized as the image of one single phi. It's only portions of the sphere. The whole sphere cannot be realized for obvious reasons because this, oh, I should also put that phi is 1 to 1. The local surface definition, you have to add that condition 1 to 1 also. But anyway, the point is that the whole sphere cannot be realized as the image of one single phi because U is an open set in R2 and S2 is compact. So phi cannot map this onto that in a open set cannot be injectively mapped onto a compact set. Right. Now, in the last few minutes, what I'll do is I'll quickly try to describe the notion of a curvature of a surface, which was Gauss' major discovery. Because here the curvature definition is not so obvious. There are two candidates which I'll mention. One of them is the right one in some sense. Both are quite important. But the obvious definition of curvature turns out it's not quite the right one for this study. So let's start with the two definitions of curvature. What we'll do is, so first let's define a tangent vector. So let S be a surface in R3. So when I say a surface in R3, I forget about the maps, the phi. I just look at the image. The image is all that I'm concerned with. The map no longer plays a role. Let S be a surface in R3 and P be a point in S. This is S, this is a point. I want to define a tangent vector at P. A tangent vector at P to S V is a tangent vector at P to S if V equal to sigma prime 0. Basically, I look at a curve lying on the surface and take its derivative for some sigma defined on small interval into S, sigma 0 equal to P. So if I want to get hold of tangent vectors, all I do is I'll just look at curves passing through P at time 0 and then just take derivative of the curve. That's the most obvious way of getting hold of a tangent vector. So if you do this, for example, for the sphere, you will get for next definition is the tangent space to S at P is the collection of all tangent vectors at P. So for example, if you do it for the sphere, let's take P to be this north pole, then you will just get all these vectors. Of course, the picture is slightly misleading because you will get the set of vectors is not an affine subspace like this. You will get it here. So there's some slight subtlety there. But the fact, let's take it as a fact, but this way of defining tangent vectors has one problem. It's geometrically quite clear, but the problem is that if you look at the set of all tangent vectors, it's not clear if it's a vector space, but in fact it is so. Fact is that the tangent space, so this is denoted by TPS. TPS is a two-dimensional vector subspace of R3. Now next I'll come to curve. So what I'll do is now I'll again take a point P. Let's take a tangent vector. I want to somehow define the curvature, how curved the surface is at that point. So what I'll do is I'll fix a normal vector. Let n be a normal vector at P. By definition, n is a vector in R3 which is perpendicular to all tangent vectors. Inner product is 0 for all V in TPS. So there are two choices, either this one or the one pointing below. This is N. Now I look at the two-dimensional plane spanned by these two vectors. Spanned by these vectors, based at this point. So it will give me a, let WV be the two plane spanned by N and V. So the intersection is this. The intersection will give me a curve. Intersection of WV and S, at least close to this point, will give me a curve. There is a curve in W. So this is WV, this two plane. So then you just look at the curvature of this curve. So forget about R3. Now we are back in the two-dimensional situation. So you have a plane which is WV and you have a curve. So you have WV, you have a curve here. This is the point P. Then this is the initial vector V. So you parameterize the curve in some way. So let this curve be, call it sigma. Sigma. When I say sigma, of course I mean the image of sigma. So sigma is some curve. Then what I'll do is the usual construction. I'll look at sigma double prime t. So I'll assume sigma is unit speed. You can always ensure this. Then whenever you have a unit speed curve, if you differentiate this, you will get sigma double prime t equal to 0, just product rule for derivatives of curves. So sigma double prime t is something perpendicular to this. Well, here you already have n. So sigma double prime t is perpendicular to the tangent vector. So it is some multiple of n. That fixed vector n. Now here difference between this and what we are doing earlier is, of course, if I take norm here, I'll just get modulus of k. But now this can have a sign. The earlier definition didn't have a sign. Now this can have sign. K is curvature along V. Let's just give it some name like that. So what we can do this for every tangent vector. You do it along all tangent vectors. You just look at the normal vector, look at the two dimensional subspace, intersect, get a plane curve, do this construction. So you'll get some number, which may be positive or negative or 0. Now the thing is, it turns out that there is a direction in which this quantity is maximum and there's a direction in which it's minimum. That's not very surprising, but actually those two directions will be perpendicular also, but that's not needed. So fact, so let's call it as, let's denote it by KV. There exists V1, V2 such that KV1 equal to max or sup of all KV, V in the tangent space, and KV2 equal to inf KV. I'll just finish in a couple of minutes. So this is, okay, so these are called principal curvatures of the surface at P. So there are Gaussian curvature of S at P is defined to be the product of these two. The mean curvature of S at P is defined to be the sum of these two. Now, as I've defined it, there's no particular reason why one should have anything significantly different from the other. You just got two numbers, you added and multiplied them, that's all. But as it turns out, this is somehow the right definition, not this, for a candidate for a curvature of a surface. Because the main point is that Gauss made this discovery, remarkable discovery, that if two surfaces, if there is a function from one surface to another which preserves distances on the surface. I haven't defined distance on a surface. I was going to do that, but I'm out of time. If you have function from one surface to another which preserves distances on the surface, then the curvature, Gaussian curvature of one surface at one point and Gaussian curvature of the other surface at the corresponding point will be the same. Not so with the mean curvature. So if you can distort one surface to another while preserving distances, they will have the same Gaussian curvature, but not the same mean curvature. And since the whole study of Riemannian geometry is based on properties which are preserved by distance preserving transformations, obviously the first one would be the right choice. And ultimately I was going to lead up to an interesting theorem which would relate Gaussian curvature of a surface and the topology of a surface. Just like that earlier Fari-Milnor theorem, there is another fundamental theorem here, but I am out of time, so I will just stop here.